Okay, we are moving to the next presentation. It's hard to get everybody from discussions and coffee, but it's very important to talk to each other during the breaks, and we have lots of breaks, but we also have lots of presentations. So I'm glad to introduce to you Mr. Olivier Attier from Tenkate Geosynthetics, and he's giving a presentation together with Patrick Pinet from Geophy Consult, and it's about early detection of dikes and dams anomalies. Who do I give the...
Okay, thank you very much. Thank you very much, Nico. So ladies and gentlemen, good morning. So it is the first presentation concerning the sensing part of this big network solution, and we will present in fact what is possible to do with optical fiber measurement. So before starting deeply, I will introduce just our both companies. So Tenkate, so perhaps some of them know, we are producer of technical textile in different field of application, and especially safety, space, sports and landscaping, and also all what is related to infrastructure and environment. And in fact, the part which is corresponding to this sensing solution comes from this infrastructure part. I leave Patrick.
Okay, so nice to meet you. Now I'm going to introduce the company I represent, which is a startup. In fact, we are introducing innovations which are aimed at managing the erosion risk, because unlike some people around may not know, about more than 80% of dam failures are not due to mechanical instabilities. They are due to internal erosion, which means processes which are in progress within the dike, which have no signature on the surfaces. And what we are doing is just to assess the vulnerability to erosion via new erosion tests, which enable to have a first quantitative estimate of the vulnerability to erosion of an embankment, of a given embankment. And we are also working, and this is why this will be the topic of this presentation, about the detection of early signs of erosions via fiber optic surveillance, which means that we will dig within the structure a fiber optic, which will be linked to a position near the dike, and via internet or any other reliable telemetric sense system, we can have an assessment of what is happening within the dike. So, as you may know, there are many needs to monitor earthworks, because they are very sensitive structures. They are subject to meteorological events. Of course, it is also requested to have an optimization of these structures. And during construction, it is very important for many practical aspects to have a follow-up of the structures. But it is not limited to standard earthworks. It can be applied also to hydraulic works, because especially of floods, which is something which is very important in here. As you can see here, there are many floods. Of course, the last one in Wilnis in the Netherlands, but also in America, in France, or in any places all around the world. And as you may know, generally, how do we manage the risk, the safety of those structures? We manage them via two things. First, the structure, which is supposed to be designed so as not to break, but in case it breaks, in case the defense barriers have a problem, we have to monitor what is going on within the structure. And it turns out that the conventional monitoring methods, like telemeters, piezometers, electric gauges, etc., are generally very complex, and hence they are not very reliable over very long periods of time. For a dam owner, he's not talking about years, he's talking about decades. He wants his system to be reliable for 20, 50 years. And over 50 years, if you have an array of sensors, then the reliability as well as the maintenance cost is something which will be considered as very, very important by the dam owner who pays. And the conventional methods generally are not adapted to that. Therefore, besides, it happens that sometimes the other conventional surveillance methods, which are especially the visual inspections, they turn out not to be able to detect internal erosions that were in progress within the dike, but when we could see that they were occurring, it was too late so as to secure the dike. Therefore, the disaster could not be prevented. Besides, some of the dikes should have a water tightness because of economical reasons, like for instance dikes for water supply. And it turns out that it is very difficult to ensure that the leakage are actually beyond the specifications of the water tightness. So, in other words, the fact is that there is a need for new monitoring technologies within dikes. And there is one parameter which has not been mentioned really up to now, which is the temperature. The temperature has been known as a very good indicator of leakage within embankment structures for a very long time. In particular, we have most of the time, if you have here the water and the dike, we generally have piezometers, and if we make a thermal profile, we know that it is a very good indicator of leakages like this one, which is here depicted. The fact is that temperature can be very easily measured by a fiber optic. If you have a fiber optic, you will send here within the fiber optic an optical signal. As you know, for telecommunications, this optical signal, 99% or more, is transferred without any reflection. However, there is a very small part of this signal which is reflected each time it is seeing an atom. And this very small part of the optical signal which is reflected according to the local temperature around the atom as well as the strain around the atom. And if we have a system which is able to measure the signal, the reflected signal, an electronics which is able to measure it, this electronic, provided it measures the time at which the signal comes, it can locate where it happens, and with this you can have a very cheap, very reliable way of measuring the temperature within the dike around the fiber optics. And therefore, surveillance-based based on fiber optics happen to be a combination of the measurement of a parameter which is intrinsically adapted to the detection of leakage within an embankment structure, and which is very low cost. When I'm talking about low cost, the cost is around, to have an idea of the raw fiber optics, it's a question of euro per meter, so something which is very affordable. And it is very reliable, so it has a great potential. So, so if you go in more details, the kind of precision that we can get is that we can have a measurement every 10 minutes, and we can locate with an accuracy in space which is 1 meter, and with an accuracy in temperature which is around 0.1 Celsius degrees. So as I pointed out already, it can be installed anywhere. You have to dig it, you can put it within the structure without destroying it. It is very low cost, it is passive, so it means that there is no long-term drift, there is no sensitivity to electromagnetic or radioactive noise. This is why it can be used, it is also used in nuclear power plants, and it can be easily combined to any other products like the geotextiles that my colleague will talk about later. And last time, it's very stable over several kinds of years. And in case you use another phenomena, optical phenomena, you can also measure, as I told you before, the strain with an accuracy which is about 20 microstrains. So it can be used for settlement measurements, passive settlement measurements. The other advantages of it, So now if we go into more detail, how can we use the temperature to detect leakage? In fact, when you have a leakage, you will change the thermal regime. You will go from a conduction regime, which is something very well known in physics, and it will change from convection to advection. And this thermal change regime can be very easily detected with automated algorithms. So this is why we use this change to detect the leakage as soon as they initiate within the structure. So then the next step is, how do we position the fiber optics? It will depend, in fact, on the structure. For instance, if we have a zone dam with a water tightness, we will try to install it below the water tightness if it is possible. Or we can also install it on the raised berm. It depends on the structure. It is very important because the access radius of the fiber optic, it will intercept any leakage within around 1 meter around the fiber optics. And with this, we can detect anomalies of the order of 0.1 Celsius degree over 1 meter every 10 minutes. And our return on experience on actual structures, real structures with EDF, is that we can detect leakages that can be as little as 0.2 liter per minute per meter when it is positioned on a drained upstream facing, and of the order of 1 liter per meter per minute when it's installed down on a downstream facing. Which means that for most of the erosion risk, it enables to secure the structure before failure, unlike all the other methods. So if you want to have an idea of what kind of signals you will get, you have here, for instance, a leakage. You will have here your optical fiber, which will intercept it. And you have here the time, which will go over time, and here the distance. At the beginning, you have nothing until a thermal anomaly is occurring, and therefore you can locate it with time and with space. And with deformation, it's exactly the same. You will also locate it in time. It occurs at that time, and in space, you have an anomaly here as well as there. I was presenting you the raw data. We can also work on more complex data with more complex data analysis systems, and then we can have anomalies where we can create some precursors, locate them in space, and here it's a picture at a given time. So with this, as you will see at the end, we are able to have a leakage precursor detection and as well a monitoring of the evolution of the anomaly in space and in time. So in summary, those fiber optic systems are able to prevent or at least drastically reduce the risk linked with internal erosions. We can also use another technology which is combined to heating around the fiber optics, and then we can have access to the leakage flow rate. However, then the access radius will be reduced from 1 meter to about 15 centimeters. Of course, and it's very important here for urban flood, it can be connected to internet via basic PC, so it enables to have automated alerts and alarms. And it can be used for repeated measurements as well. So in case a dam owner has to have a period of time where he has to reduce his running cost, you have paid the investment, which is very low and still active. The only limit are the following ones. The system, the instrumentation, cannot go beyond 30 kilometers, so it means that you have one investment per each 30 kilometers period. And if we want to reach the detection threshold I was mentioning before, then it requires detailed design and advanced data analysis, which means it details actual skills. So now I'll give you my colleague.
So Patrick show you the fundamentals very shortly, the fundamentals on optical fibers. And from this starting point. So from this background, we have developed a solution for geotechnical application mainly and hydraulic construction, which is a combination of a structural barriers, so a filtration geotextile, which prevent the soil erosion, internal erosion, in combination with a monitoring barrier based on sensor and optical fiber sensor. So the principle is the following: on this textile, which is used commonly to prevent erosion, we embed several optical lines which are able to detect a leakage or a strain or an abnormal deformation in the dike. So there are two different possible measurements, either stability control to detect slippage or settlement of the dike, or it is a possibility also to detect water channel. The product is in fact the combination, as you can see, and there are other samples on the table at the exhibition room later. It is a combination of optical cable on a textile, which gives several advantages. First of all, of course, we can embed several optical lines, and we can make a multi-parameter measurement, strain and temperature at the same time, which creates a big advantage due to the fact that the textile has a good friction interface with the soil. And with this very good friction interface, we can detect the very small strain from the soil and able to detect the small movement of the work. Of course, there are all the textile functions, which are drainage, filtration, and reinforcement, that can be used also in this solution. So, in fact, the system, the sensor is produced online, combining both optical fiber and textile at the same time, and it is presented as a rule, as it is like that. In fact, this development started a long time ago, in 2002, when we wanted to reinforce and detect cavities in subsoil under infrastructure, for example, railways, roads, and so on. So by reinforcing, of course, if a settlement or if a cavity occurs, we are not able to see from outside, and due to the fact that the geotextile with the reinforcement function embeds optical fiber, this can create a warning to the control room, so that something happened in this area. So this solution was used in 2004 in several sites. We have either a bridge abutment reinforced with textile over a river, or a railway line over cavities. So, and it is working very well since this period. So the 10CAT geodetect solution, it is of course the sensor with, of course, the related optical interrogator that can be different depending on the parameter measure, either temperature or strain, and it is the measure and the data analysis. So the main purpose is early detection, localization. So as Patrick said, we can localize the event at 1 meter space resolution, which is very low when you think on the tenths of kilometer of measurement. And of course, we can create either a warning or simple monitoring of the work. We detect either strain or temperature. Temperature is for leak detection, and we can use different type of technologies. I can present now some example of this solution. We spoke already of the IDIC project, so you will have some pictures again. So of this first test in 2008 on microstability, where we have embedded and installed 4 strips of this material, so lengthwise the dike at different level in this dike, and so you can see the picture of the different installation stage of these strips. These strips are connected all together by splicing and connected to the optical interrogator. Here you can see once again the strips. So it is the top, the middle, the toe strip, and the strip which is on the field. And here you have the distance from 0 to 100 meters, which was more or less the length of the dike. And we have plot here the strain, the relative strain. We started the measurement at this date, so 23rd of September, and then the experimentation started. And we are here 2.5 days before dike collapse, and we already can see some strain in the soil here on the 2 first strips, and the hours passing, so 2 days before failure, there is increase of the strain, another strain area appearing on the 2 of the dike, here some compression zone here, and once again 1 day before collapse, we can clearly see the movement of the soil of the dike, which correspond exactly to what was observed when the dike failed 1 day later. So as from this test, performance is a 2-day detection before the dike collapse with resolution of strain which is very, very low due to this friction with the textile on the soil. It is 0.02%, which is very, very low. Another project, so this development started in 2004, 2005, and we did experimental basin in the Sémagref in Aix-en-Provence, where we have in fact install artificial leaks through the dike to control the leakage through the dike and to have a better estimation of what is the minimum resolution and performance of this sensor. In fact, you have the installation of this panel with optical fibers. The fibers are installed here. And we have created behind artificial leaks, and you can clearly see that the leaks here appear. So here is the start of the basin film, and you can see the change of temperature here due to the leaks. And of course, we can detect these leaks before they are visible from outside, and it is the purpose of this early detection phenomenon. And the last presentation, last experimental site.
Okay, so now we are once again going to talk about the iDike project, but this time it's on the piping experiments. So in fact, there were 2 basins, and here were the experimental dikes, which were broken each time, which were broken in 4 experiments. So you have here an image of a dike before it is ruptured. So you have the water here, you have the experimental dike here, and of course the basin where the water could be recovered after failure. So when it was failing, this was the kind of images, and we had the opportunity to install our system within the dike prior to their construction. So at the interface of the sand and the clay, we installed 4 strips of different kinds of fiber optics, including the geodetect fiber optics. And what we did was just to measure with time, so the temperature over surfaces like this. So I will show you here the kind of images we will finally get. It's a movie which will change every hour or every 10 minutes, and you will see the evolution of time of a temperature with time. And if you go at the end, for instance around here, when we will see here the leakage which is in progress while nothing is visible outside. And with that kind of measurements, you can have precursors that are visible from 2 hours to several days in advance, before the visual inspections could detect anything. The visual inspection or any other kind of surface surface sensors. And if we apply the EDF algorithms so as to predict with more accuracy in time the precursors, we could locate them 4 days before the rupture on an experiment which lasted no more than 5 days. So it means that with these kinds of stuff, we are able to predict with a high accuracy. And we can do the same for other experiments when we have here the temperature as well as here at the same place the strain, and you will see, and I have finished, you will see here the signature within the dike of both the temperature and the strain. So it is a tool which enables to detect it with high accuracy.
Just before concluding, the example of we have installed not only in experimental project but in a real project. For example, go too far. In fact, we have equipped 1 kilometer dike along the Loire River, a flood protection dike with this system. Also some, sorry, again, this Loire River dike. Also a canal along the Marne and Rhine River, 100 meters long, where we, in fact, this area was suspected to have leakage, and we have, of course, detected the place and the location, and more or less quantified the amount of this leakage. Here you have the picture of the leakage detection. Also, we have recently installed close to Amsterdam the so-called Volga-Mer area, where the purpose was to measure the strain in this basin due to the filling. And also, Patrick is ongoing to make a study for the French waterways along the Rhine River to study the implementation of optical fiber solution on 38 kilometers of dikes. So to conclude, so you have seen that this early warning solution based on optical fiber is a very powerful solution. Can be automated for surveillance of dam and dikes. They can predict failure with a very high accuracy and high space time. By combining with the textile, this enhance the power of the optical fiber solutions that can be detect both strain and temperature at the same time. And it is reliable, easy to install, durable, and it can make multi-parameter solution. And when we apply with a specific algorithm or modelization for data analysis, we can enhance very well the early warning system. Thank you very much, and sorry for the little delay.
Okay, we have a very tight schedule, so if a presentation is too long, we don't have much time for questions, but I'll allow 1 or 2. Okay.
How do you actually differentiate between a temperature and a strain measurement?
There are two physical phenomena. One is measuring directly the temperature, and the other one is measuring both. So if you use both phenomena, which is the Raman phenomena, both on the one hand, and the Brillouin phenomena on the other hand, then you can dissociate both. Besides, the sensitivity of temperature with the Brillouin technology is quite little. Therefore, it's to the first order mainly sensitive to the strain. It is actually not a technological problem. It has been solved by the electronics systems.
In fact, it's not exactly the same fiber. That's why we embed several fibers on the textile, so that one fiber is related to temperature and the other one is for strain measurement.
Fibers have a different response.
Yes. Okay. One last question. Okay, if not, thank you very much again.